Here is reported a brief summary of my presentation. I will discuss about some basic concepts of fatigue failure, and then I'm going through a review of main stress life curves for axial fatigue failure assessment. There I'll show a fatigue assessment with an application to a real case study, and then I'm going to go through the conclusions. As you know, the fatigue failure became an evident problem during the Industrial Revolution in the 19th century. It was recognized as a fracture phenomenon occurring after a large number of load cycles, where a single load of the same magnitude would not provoke any kind of damage. Firstly, it was recognized and occurred in some different systems from structures, such as steam engines, locomotives, airplanes, and pumps. So it seems to be so far from civil engineering. As well, as I told you, when we are imposing an alternating load, we provoke fluctuating stresses. These fluctuating stresses consist of a minimum maximum value, and the maximum value may provoke a fatigue failure that is significantly lower than the monotonic strength. When the fluctuation is imposed, we can recognize, for instance, the stress ratio that is called R, that is the ratio between the minimum and maximum stress imposed to the material, to the component, the mean value, the stress amplitude, that is difference between the maximum and minimum value. Questo? Sì. Okay, thank you. We can define the mean stress, the stress amplitude, or the stress range. That is simply the difference between the maximum and minimum value of the stress imposed. Here I reported some simply case regarding fluctuation stress when the minimum and maximum value are different from zero. The simple case when we call it reversed stress if the mean value is equal to zero, and the case of repeated stress if the mean value, the previous one is reversal stress when the average value is equal to zero, and the last one is the repeated stress when the minimum value is equal to zero. How we can assess the fatigue behavior of a component or of a material? Usually we use this tool that is a data chart called the stress life curves, or else SN curves or Wöhler curves. In this data chart, we plot the cycle stress magnitude or the fluctuation. It depends on how it is proposed, the stress life curves. And this data chart provides in linear log normal scale the number of cycles at failure of a component or of a material. In the same data chart, we can recognize as well the fatigue or endurance limit, that is the maximum stress that be applied, below which the failure for fatigue does not occur. And for measuring how far we are from the fatigue failure, usually in the literature is used the Palmer-Crane linear damage rule. It is defined as the ratio of the number of cycles applied over the number of cycles corresponding to the fatigue failure of the alternating load considered. And this is a fraction, and it expresses as well the amount of life that is used by the fluctuation imposed. When the sum of the damage fractions are greater or equal to 1, we say conventionally that the fatigue failure occurred. So despite its importance confirmed by some experimental results that I will show you later, currently the fatigue behavior of masonry structures is still poorly understood, as confirmed by the lack of appropriate procedures in many design codes. For instance, in British codes, it is reported a rough limit for preventing the fatigue failure, corresponding just imposing that the maximum load that may be applied should be less than 50% of the ultimate vertical load imposed. Somewhere else instead is found the indication, the rough indication that the 50%, there is a limitation of 50% of the static strength applied. So we know that not necessarily to the 50% reduction of ultimate vertical load does not necessarily correspond to the same percentage in static, the maximum level of stress applied. Elsewhere, for instance, in the Euro codes and Italian standard codes, there are only reported some indication for steel elements for evaluating the fatigue assessment of the components, including as well some stress life curves for both axial and tangential stresses, but nothing for masonry. So starting from this really simple insight, we think that the evaluation of the maximum level of traffic load related to fatigue limit state may be really important rather than the ultimate capacity, becoming particularly important in the case, for instance, in the case of unsafe brick masonry bricks. So in literature we can find a series of experimental tests in which the main aim is to propose some stress-like curves, mainly of brick masonry. Here are reported some of these investigations. The first that I'll show you is the stress-life curve proposed by Ronca. The main feature of this experimental campaign was that the maximum load applied was very high, ranging from the 65 up to 85% of the ultimate compressive strength. And they proposed a stress-life curve that is really simple, linear in the logarithm of the number of cycles applied. Instead, a more extensive formulation was proposed by Robert, starting from another and a different kind of experimental campaign, so in which experimental campaign were tested several types of masonry specimens, considering also the case of eccentrically loaded specimens for taking into account the case of masonry arches. They proposed a more extensive stress-life curves, including as well the R ratio, that is the ratio between the minimum and maximum stress imposed during the alternating load. And this relationship is as well linear with the logarithm of the number of cycles imposed. Starting from the previous results, Casas re-elaborated these results for proposing a new stress-life curves. These stress-life curves are based on a probabilistic approach. This means that the authors proposed a relationship in which the coefficient in a nonlinear equation are related to a certain probability of survival. And there is as well, by the same author, a tentative of including the effect of the fatigue strength through the tangential stresses into the stress-life curves. Another interesting and comprehensive campaign was carried out by Tomor and Vestringe, is more recent. Here as well, the relationship of the stress-life curves is linear, including the R ratio, and the analytical formulation is quite similar to the one proposed by Casa, slightly different in terms of coefficient, but is as well based on a probabilistic approach. And finally, there is this really interesting experimental campaign. The main characteristics of these results is that the formulation was proposed based on some fatigue cubes derived for low-strength masonry prisms, brick masonry prisms. So this case is really a case to the existing masonry arch bridges, for instance. Here, as well, there is a probabilistic approach, and there is a nonlinearity between the maximum stress that may be applied and the logarithm of the number of cycles imposed to the material. Here, just an overview of all stress-life curves considered in this study. The first two are based on a deterministic approach. Instead, the other ones are based on a probabilistic approach. So it's quite interesting to compare all of these stress-life curves. Here the comparisons is made in a graph in which on the horizontal axis is reported the number of cycles at the failure, and on the vertical axis is reported the ratio between the maximum stress applied over the ultimate stress, for making all of them comparable each other. Here the comparisons are made for 4 different values of the R ratio. I should remember that the R ratio is the ratio between the minimum and maximum stress applied. The higher the R ratio, the closer the stress is applied during the fluctuation imposed to the material. We can recognize, for instance, that the models provide fatigue strengths that are not in agreement, except for the case here illustrated for the ratio equal to 0.6, where the scatter seems to be really low. In other, all the models for a given stress imposed provide results that the higher the R ratio, the higher the cycles number at failure. And for the ratio equal 0.2 and 0.5, we can know that the model may predict a low number of cycles at failure, even lower than the conventional entrance limit that some studies, some research have set equal to 0.5. And finally, on the contrary, for R equal to 0.8, the fatigue strength instead is significantly higher than the entrance limit. So starting from these considerations, we investigated a real case study. Here are reported some picture of the case study. Is a multi-arch masonry bridge. Is still in service. Is serving a provincial state road in province of Matera. The bridge is named Ponte Cavone. It takes the name from the crossing river. It is covering a total length of about 130 meters. And all elements of this bridge are made of masonry, two different kinds of masonry. Piers, abutment, and spandrel works are made by stone masonry, while arches that are investigated in this study are made by brick masonry with irregular texture. So by focusing on these two type of arches of the Cavone Bridge, we went in a preliminary fatigue assessment with respect to the axial stresses acting within these arches, following the procedure proposed by Eurocode and Italia standards. Of course, I remember that these documents, no indication are provided for masonry, but only for steel elements, but we tried to apply this procedure just changing, instead of stress life curves for steel elements, stress life curves for masonry elements, the one that we gathered within the literature. How we can resume the main steps of the fatigue assessment? First of all, we should define a fatigue load model and the number of expected EV vehicles per year in according to the traffic category of the road. Then we have to numerically solve the problem for calculating the most compressive stresses within the arches, the two types of arches, from with respect to the maximum fluctuation imposed by the fatigue load. And then it's necessary to assess the number of cycles at failure associated to the stress fluctuation, but we should refer to the factorial curve that I will show you later in the next slide. And finally, we can assess the residual service life, that is the ratio between the number of passages of the load, the number of cycles corresponding to the fluctuation found in the previous steps over the number of cycles at failure provided by the stress life curves. So as for the fatigue model, we should refer to the fatigue model as defined by Eurocode, Italia standards, defined as a fatigue load model 3. It consists of 4 axles. Each of these axles consists of a vertical load of 120 kilonewton, acting on a square area of 0.4 into 0.4. And then we should define the number of EV vehicles yearly expected on this according to the importance of the road. It's reasonable in this case to assume that the road served by a bridge is interested by a traffic category equal to of type 2. This means that 500,000 of EV vehicles are expected per year passing on this bridge. Here, after defining the fatigue load model, we should find the most compressive stresses by considering the fatigue load defined. And for evaluating the most compressive stresses, we monitor 2 different sections that are the key section and the arch sections for the 2 different kind of arches considered. The numerical model was implemented into OpenSys. It was a really simple model by considering as well the diffusion within the backfill up down to the extrados of the arches. And we defined a fiber model, really simple, with a linear, perfectly plastic material with no tensile strength, even if we observed finally after the numerical evaluation that the ultimate strength was never reached in our analysis. So after here I can report the numerical results. The numerical results are reported for the 2 types of arches considered. For the main arch and for the secondary arch, we consider as well 2 knowledge levels in according to the Italian standards, the knowledge 1 and knowledge 3. That in according to this approach, so we can consider 2 different kind of compressive strength for the masonry. Here are reported the numerical results, and we found that the most compressive stress occurred for the hinge section for the main arch, at the key section instead for the secondary arch, and the fluctuation was really significant only in the case of main arch, and we believe that this results was mainly due to the backfill, to the rule of the backfill over the below the deck. Here is the reported, the fatigue assessment, graphically reported for making all stress life curves comparable each other. Here are reported the stress life curves in terms of the ratio of the maximum stress found over the ultimate strength. And here are reported all stress life curves by considering the knowledge one. So we have to check if this fluctuation, the maximum stress, cross some stress life curves. And we found that in the case of Casas, Roberts, and Colsida, we can define a certain number of cycles at failure. Instead, in the case of Ronca and Tomorrow-Stringe, the maximum stress applied was inadmissible. It means that this kind of fatigue models cannot be applied for this kind of fluctuation. On the contrary, the results drastically change in the case of knowledge 3. In this case, for all models, there is a solution, so we can find the number of cycles at failure, and the number of cycles results greater than 10 powered at 8, so a really huge number of cycles for failure. The same kind of results we have found in the case of secondary arch for both knowledge levels, knowledge level 1 and 3. As well, we have a solution in terms of stress fatigue strength, and all stress life curves provide a number of cycles at failure greater than 10 powered 8. So here are reported the numerical evaluation regarding what I have explained in terms of within the graphs. Here is as well reported the calculation of the residual service life. That is an application of the Palmgren linear rule. It is again the ratio between the number of cycles expecting passing over the bridge over the number of heavy passage over the bridge expected per each year. So here we can recognize that there is a significant scatter between the results found in terms of residual service life. The residual service life may result about 0 here, about 3 here, or about 80 here. It seems reasonable because the stress life curves are different, significantly different each other. Instead, for Tomorrow-Stringe, in this case for the main arch, no solution was found. As I showed you before, the results drastically changed in the case of knowledge 3, where the residual service life resulted greater than 200 years for all models, and this value is much more comparable with the value assumed for designing new bridges. The same results are obtained in the case of the secondary arch, where for both knowledge levels we found a residual service life greater than 200 years. So I'm going to conclude. With this preliminary fatigue assessment applied on an existing arch bridge, we can conclude that fatigue assessment may become particularly important in the case of existing masonry as bridge, as demonstrated by the application of this case study. Contrary to steel elements, no indication is present in the literature and design codes for fatigue assessment of these elements. And of course, the results are strictly depending on stress life curves involved that play a central role in evaluating the fatigue assessment of the bridges. They should be experimental, derived starting from specimens reproducing several types of masonry, for instance, bricks masonry or stone masonry, including as well low-strength materials and as well pronounced degradation. That is really common in the case of existing bridges still in service. Of course, the knowledge of bridge is fundamental. As we have seen, changing the knowledge level, the results drastically change, so there is something to be checked again. And finally, stress life curves should be dependent not only by the stress fluctuation, this is our point of view, but also including inside the lock frequency, that is another important aspect for evaluating the cumulative damage by imposed with the alternating load, and the stress amplitude imposed by the alternating load. Thank you.